Okay, yes, thanks for giving me the opportunity to present my research here. So I think I think this talk will be a little bit different from the other talks that were held in this series. So I mean, if you watch the previous videos which are uploaded on YouTube, you can see basically people talking about the impact of their research and basically why it matters in that regard. So what kind of implications does it have? Now, I interpret this title a little bit differently, partially because of time reasons, because I didn't have time to present like a very big comprehensive talk. So I'm interpreting why it matters in basically in the question, why is it interesting? In the sense that, okay, it's great that if you have a problem, if it's great if you have a problem that if you solve it, you can solve world hunger. But is this really what gets you out of the bed at like 5 a.m. in the morning and like on your desks and like pursuing this without with reckless abandon? And so basically, I just want to maybe talk about what makes a mathematical problem what makes a problem interesting in general. Okay, so this is, and I want to maybe approach this from a layman's point of view. Now, obviously, if you're an expert in a certain area, you know like what are the interesting problems and things like this. But I'm just talking about like randomly picking somebody from the street. Okay, maybe currently during the lockdown, there's nobody on the street. But if lockdown were loose, you can pick somebody from the street and you ask them, what do you think makes a problem interesting? And then there's the obvious answer, it improves society, right? So you have some positive impact, either, I mean, directly to the society, or I don't know, you basically open up new industries, which will employ people, which will give them jobs and which will give them money and then which will make them happy. Something like this, something that basically in the end will improve society. And maybe this does not need to be directly your research, but maybe your research can lead to something that basically builds up to this effect. So this is something, I think this is basically one of the main, the reason, which is why I listed it first, what makes a problem interesting. Another aspect that can make a problem interesting is it is just challenging, because we humans are just very competitive beings. And just the fact that basically a problem is hard can make it very attractive to certain people. I mean, it's like, think of like sports, how people push themselves to break records and things like this. For example, like I think one of the most outstanding recent accomplishments is Eliud Kipchoge, who managed to run the marathon within 2 hours. So that was like really impressive. But I mean, the fact that he did this didn't really solve any global problems. It's just that this is something that nobody has done before him, and he's the first human to achieve this. And this is why this is very interesting for the general population. Now, in mathematics specifically, there's a third type of interesting, and this is why I wanted to bring this up. And the third type of interesting, which I think is actually specifically more to math, or at least it's most prominent in math, is that you have a problem that is easy to understand, but it's incredibly hard to solve. It's surprisingly hard to solve. So with easy to understand, I mean something that maybe in elementary students can see, yes, can understand the general problem that you're trying to solve, but solving it is very, very hard. Now, there are two types of problems of this kind. So either you have a problem that cannot be solved. So it's a very problem that can be easily stated, but you cannot solve it. So one example famously is the Collatz conjecture, which basically states, I don't know how many people are aware of this here. If you see this on YouTube, just feel free to Google this to search for it. There are a lot of great videos on this. So this basically says if you start with a number, any integer, let's say 7 or anything, and then basically you either divide this by 2 if this was even, if AI was even, or you multiply this by 3 and subtract 1 from it if AI is odd. Or maybe it's add 1 actually, I don't know, it's plus minus 1. Then basically, if you do this with any number, you will see that in the end, you will always get like a pattern of like 8, 4, 1, 8, 4, 1, 8, 4, 8, 4, 2, 1, and something like this. And the conjecture is that this pattern will always hold, with regardless which n you choose at the beginning. And this is very famous because this is very prominent in mathematics, or maybe even a little bit in pop culture, because at one point, a very famous mathematician was asked whether he can solve this question. And I think this was like, this was not too long ago. And he famously said that mathematics as it is right now is not ready to answer these type of hard questions. So that was pretty humbling for a mathematician. But on the other hand, there exists also problems that are easy to understand, but whose solutions involve such outlandish methods that you cannot help but wonder whether an easier solution exists. So a prime example for this would be Fermat's last theorem, which says that basically for these type of equations, there exists no non-trivial solutions. And non-trivial means obviously if I set y to be 0 and then x and z can be anything, this is a solution. But besides then, what type of solutions do there exist? And this is a problem that was famously solved by Andrew Wiles and a lot of his collaborators, but using a lot of very deep, sophisticated techniques. Something that you would not expect if you look at how easy this question is. So these are basically two types of math questions which are really, really interesting intrinsically, or just because of our human nature. And I think I want to touch upon one of these type of problems that I encountered very recently. And this involves basically, this I encountered during my studies of neural networks and using tropical geometry. And let me just quickly maybe introduce what I mean with neural networks. So again, I only have, I think, like 15 to 20 minutes for this talk, so I have to cut a lot of corners and maybe even outright lie to you at some point. But please bear with it. So when I say a neural network, at least for this talk, I mean a single layered max-out network. And these are of the following shape. So I'm talking about a function that goes from Rn to Rm, and it sends x basically to a maximum of these things that you see there. So it's a1 times x plus b1 up to a r times x plus br. And I fix n and m and r beforehand, pick whatever numbers you want. Now the ai's are matrices, the bi's are vectors in Rm, and the maximum is the component-wise maximum. So that the maximum of 32,23 is 3,3. So this is basically how a single layered max-out network works. And one question that people in machine learning are interested in, at least some of them, is, so first of all, you will see that f itself is a piecewise linear function. So f itself is not a linear function because there's a maximum inside of it, but locally around almost all of the points, it will be piecewise linear. And one question that people are studying is basically how many of the linear regions can it actually have maximally. So basically, if I fix n, I fix m, I fix my r, and I vary my matrices ai's and my vectors bi's, how many linear regions can I have maximally? Now let's take a look at a couple of these examples. Sorry, I should have said beforehand, this talk is part math, but it won't be long, so please bear with it for now. This will be over in 5 minutes, this math talk part. So if you look at an example like f1, so you have a function from R2 to R, and I map x, y to the maximum of x, y. Then I can plot this function, and I can see it has two linear regions, basically a region where y is maximal here, and a region where x is maximal. So there are two linear regions overall, and they're subdivided by this one line. If I look at f2, then this sends x, y to the maximum of x minus 1, y plus 1, and 0. And I can see that it has three regions. Basically, if I pick a point, if I pick a point down here, x and y will be negative. So 0 will be bigger than both of them. X minus 1 and y plus 1 will be negative. If I pick a point here, the y component will be maximal. And if I pick a point here, the x component will be maximal. Now I can look at a function f1, f2 that goes from R2 to R2. So basically now I have two components. And what I see here is actually that this has 5 linear regions. Again, just to make sure, so let's just call this thing f here. So basically, in order for f to be linear around a point, both f1 and f2 must be linear around that point. And this is why basically the linear regions of both f1 and f2, they basically overlap. And you have basically these 5 regions, 1, 2, 3, 4, 5, where before you had either 2 or 3 respectively. Now, how do you count actually these regions? So how do you compute these regions? So one thing that these regions actually are involved with is something called a Minkowski sum. So basically, how do you actually determine what these regions are? And this is basically shown here in the bottom. So basically what I can do, so let me just scroll up for that. So if I look at x, so if I look at this point, so x itself is, I can basically be written as 1, 0 times xy. Y can be written as 0, 1 times xy, and this 1, 0 and 0, 1 is something like an exponent vector if you have a polynomial. And similarly, the 0 on the right-hand side can be written as 0, 0 times x, y. And what you can see is if I, for example, on the left-hand side, if I look at this 1, 0 and 0, 1, and I draw them here into this picture, I get something that is like dual to the picture that I have here. And similarly here on the orange part, if I basically draw this 0, 0 that I get from 0, and then this 1, 0 and 0, 1, and I basically connect them together, I get a picture that is somehow like a complement of what I've just drawn there. And this is something that's referred to as duality in mathematics. And what you can actually show that is that if you basically add these two shapes together, and this is something that's referred to as the Minkowski sum, I get something that's dual to basically what they overlie. So if I look at basically this shape again that I'm just drawing here, I can basically find a subdivision so that the dual picture looks like something that I've drawn on the right. So what I'm drawing here, so the black thing is basically something that looks like the blue and orange thing on the left. And basically the composition of the linear regions is basically dual to the Minkowski sum of these polytopes that I've drawn. Okay, and the Minkowski sum is just, it's a very simple intuitive operation. So basically, if I have two polytopes, which basically is the convex hull, so it's basically a shape, let's say in R2 that you see here, it's a line, it's a triangle, or it might have 4 edges or 5 edges. The Minkowski sum is basically just you take a point in the first one, a point in the second one, and then you add them together and you get a point in the third one. And this is how these shapes will basically add together. Now, this might look very complicated, but it's actually quite intuitive. And I will just run through a lot of examples and hopefully make clear that this is quite intuitive. But before that, I just want to point out that basically now the question, how many linear regions this have, is kind of related to basically if I fix these polytopes and I look at the Minkowski sum, so what's on the right of this equality, how many vertices can this thing have? So these are basically these what I've circled red, because each of these vertices will correspond to a linear region in this dual picture. Now, what are these Minkowski sums? So here are a couple of examples how to compute them. So actually a lot of examples. So for example, if I look at the top, so if I add one line segment to the other, then all I get is basically just a square. Or I mean, if let's say if they're a little bit, if they're not orthogonal to each other, I would get something that looks like this. Right? You just basically kind of take the sum in a very intuitive fashion. I can add 3 line segments together. I would get a shape like this with 6 edges and 6 vertices. I can also add basically a line segment to a triangle, and I would get something that's on the right-hand side. And you can see this, basically the sum that happens, it's basically you take a triangle that you have here, and then you basically move it around left and right based on the shape that you have here, and it will draw out a shape that's like on the right-hand side here. So it will have 5 vertices, 1, 2, 3, 4, 5. You can add a triangle to a square and you would get something like this with 6 vertices. So basically these adding these things themselves is actually quite, I would say, a natural operation. And the question that I have basically that I hope is not hard to understand is basically if I fix these polytopes here with a fixed number of vertices, how many vertices can there be on the right-hand side? So for example, in this case, I have 3 vertices here, 1, 2, 3. I have something with 4 vertices here. How many vertices can there be on the right-hand side, maximally? Now, in this case, it's 6, but can it be 7? Can it be 8 if I change the shape on the left-hand side? This is the question that I'm trying to solve. So, okay. Now, the answer is also relatively, well, I guess relatively simple, but I guess it's actually quite hard. So if you look at this and you try to find a pattern, you might come up with a formula like this. Oh, sorry, I didn't even write that down. Okay, this means then we have to improvise. So the answer is, let me just think. I think it's m minus 1, choose n, plus, I take a regular sum from j equals 0 up to n, m choose j, r minus 1 to the power j. Very, yeah, very simple, very complicated, depending on what your point of view is. But anyways, it's basically maybe a little bit more complicated than you would expect from such an innocent question. And the question is, how can I actually prove that this is the correct answer? Now, this is where I need to step back a little bit and talk about the outlandish methods in the last 3 minutes that I have. And this is what I refer to as basically taking a sledgehammer to crack a steel nut. Because even though what I'm about to say sounds very outlandish, please be aware that these are the only tools that we have right now in order to solve the problem. There exist. I really wish there would be an easier solution, but if it is, it's basically beyond my intellectual capabilities of finding them. Okay, so for that, actually, you need to use the tool of abstract algebra, and it's a lot of symbols. So basically, what I'm trying to say is for the people who don't have a math background, so abstract algebra is about studying structure in a way. And in particular, I want to focus on two things. It's a group and a ring. And a group is basically, whenever I say group, just think of the integers. It's basically a collection of numbers which I can add to each other. So this is what it says. And the first thing here says that the order in which I add them doesn't matter. I can add the first two and then the third one, or the second and the third and the first one. My collection must also contain a 0 in there. So something that I call 0 in the integers and the rational numbers, this would literally be 0. But if I basically think of any other group, this can have some other name. But what this object must satisfy is if I add it to something, it will not change it. And similarly, as a third one, every object in this must have a negative, in quotation marks, which is a different object in there, which if I add it to it, I obtain the 0 that I mentioned previously. So this is a group. And again, it looks a little bit weird, but whenever I say group, just think of something that has an addition and behaves how you would consider addition to behave. A ring is an arbitrary set that is an object that has an addition and a multiplication, and the addition behaves like a group that I mentioned before. And in addition to this, multiplication behaves like we would expect it to behave. So first of all, it's again associative, and also it needs to be distributive with respect to addition. So a times b plus c is equal to a times b plus a times c. So this is what we call distributivity. And again, think of the integers, think of the rational numbers or the real numbers. But there are also more types of rings, such as, for example, polynomials. So if I take polynomials in x or take polynomials in x, y, z, so these are all rings. Now, the method with which these things were proven, what I said before, is basically by tracing things back to abstract algebra. So for example, Fermat's last theorem was proven using certain areas in what's commonly referred to as algebraic geometry, where I basically look at some geometric objects, such as this set that you see on the left-hand side. So this curve, this black that you see here, are basically all points in R2 which satisfy this equation. So for example, this point here would be 0, 0. Yeah. And basically, in order to understand, so at some point in algebraic geometry in the history, people want to study these shapes, but the problem is that they didn't have any tools to study these shapes because, well, there wasn't anything to work with. So what they did is they actually looked at the abstract algebra that arises from it. And this is basically now a polynomial ring, modulo this polynomial. And this modulo this polynomial just means that if I have a polynomial like y squared minus x cubed minus x squared, that this is equal to 0. Equal in the sense that basically think of this curve again, which is the set of all points which satisfy this equation here. So if your point on this curve, for you, this polynomial and this polynomial are literally the same. because you evaluate to 0. That's what this curve was. So this is why basically this is an, this is why people look at this type of algebra here. And this is still a well-defined ring. You can add 2 things in here. You can multiply 2 things here, with the small caveat that sometimes your expressions just become 0 out of, surprisingly. Now, if you're on the left-hand side, you can probably intuitively realize that this curve that I've drawn here is one-dimensional because, well, it's literally just a line. It's a one dimension. It doesn't have 2, but it's also not 0-dimensional. Now, in abstract algebra, you can find that you can also define, there are multiple definitions of how you, of dimension. And in this case, they all coincide to be equal to, not 0, sorry, equal to be 1. However, these different definitions, they might not coincide in more exotic rings. So, I mean, this is a very nice ring. It's a polynomial ring, but there can be basically more exotic abstract rings on which they don't coincide. And basically, this is something that you have here on the algebraic side that you don't have in the geometric side. These algebra things, they have many more structures and properties that are like kind of hidden geometrically. Now, once you find these properties and structures, you can interpret them in terms of geometry. However, basically, they are much more visible on the algebraic side, but you can basically see by the fact that they have been found algebraically first, and then the geometric interpretation came afterwards. So, for example, one of these properties is that all these many notions of dimension that they happen to coincide, which is called co-Minkowski. Now, in order to prove, and this is the end of the talk, in order to prove the combinatorial part, you have to do something similar. And I just want to mention that this is not my work. It's far from my work. So this is something referred to as the Stanley-Reisner ring by Richard Stanley. So this is something that people have developed decades ago, where they basically show that, okay, if you have a polytope, like on the left-hand side, you can associate to it an algebraic object, and that's referred to as algebraic combinatorics, which is basically a polynomial ring where you have a variable for each vertex. So for example, for this V4, you have V4 in here. So you have as many variables, which were called XYZ before, as you have vertices. And now you need to mod out a certain equation. And this equation basically, so this basically says that if you don't have an edge, for example, between V1 and V3, then V1 times V3 is equal to 0 in your ring. And then it turns out that basically a lot of properties, combinatorial properties that are maybe a little bit hidden on the combinatorial side, are actually clearly visible on the algebraic side. And basically, the only way in order to get a simple an answer to this seemingly simple question that I've posed here before, basically, how many vertices can it have? The only current known answer basically involves studying these complicated abstract rings that arise from these structures, and then you basically build a lot of methods upon them. And then in the end, you hope that they will add up together and you will get basically this answer that I have below here. It's this simple number. Okay, thank you very much. That's my talk.